Hi, I'm Mark Weissman. Welcome back to Quantum Field Theory, a Student's Perspective. And just to remind everybody, of course, this is like a flip MOOC course. So I'm assuming you've read the chapter in Czernecki's book, and I'm just sort of going over the high points here, because if you haven't read the book or some other book, it's pretty hard to understand most of what I'm saying. I want to finish on path integrals in quantum mechanics, and we're going to eventually relate them to quantum field theory, and the next two sections do that. But I want to finish with this one just doing what's in the book. And we start by remembering the LSZ reduction formula. This is like the most important formula in scattering and quantum field theory. And I'll just write it down briefly. I'm not sure if this is a different K. I have a feeling it's a different K, but in my notes I wrote it down as the same K. Then multiplied everything by the time-ordered product of the fields. So this thing over here, this is our key thing in quantum field theory. And one of the things I want to do in this last or next to last video is I want to relate everything we've done to this thing. And because then we can just plug it into this formula and we get the scattering amplitude. So the first thing we can do is we can extend the let's go back to our path integral equation from last time, which we've used. I've written down several times. Remember, the capital D's just hide a lot of funny factors in the measure. Relates to the fact that the path integral is ill-defined. And this is the Lagrangian. So this is the path integral formula, and this is when we have our p squared over 2m plus v. We can replace this by the Lagrangian. We can do the integral over the momentum p. So what I want to do is I want to take that formula in there, and I want to start putting operators in there. So let's write down what we have. Let's put an operator. This is an operator at time t1, a position operator, just as an illustration. Now, using the these here are Heisenberg picture states, and this is a Heisenberg picture operator. And using again, this is a Schrödinger state. Then So if you substitute these two things in here, you're going to end up getting that's not what you get. Okay. So I'm just substituting here. Now, in evaluating this path integral, basically if we go through the whole derivation that we did, basically we're going from q prime, and then we're going to end up at time t1 here, and then we're going to go like the rest. So the only effect of this is to add q of t1 to our path integral formula. So this ends up being equal to remember the action S is just shorthand for okay. So this is one way to get an operator to correspond. Here we have the operator inside of the amplitude, the states for the transition, and we see that it just brings down a q of t1 e to the is. But more importantly, this will lead to this formula. Now what's going on here? Of course, I left out something very important here. So now we have what we wanted from over there, the time-ordered product, but where did it come from? Well, you can see here that if T1 is greater than T2, this ends up just being Q of T1, Q of T2. That's the definition of time order. And so it sort of makes sense. When we're doing our path integral, the first thing we're going to do, we go from earlier times to later times. So the first thing we're going to hit is the earlier time, Q of T1, T2. That's where we get that. Then we're going to hit the Q of T1. That's where we get that. But if T1 is less than T2, then over here we're going to get the opposite order. And we're always dealing with bosons to start, so don't worry about minus signs on the fermions. So now we're going to get Q of T2, Q of T1. And that's what we want, because T1 is the earlier time, so the first thing we're going to hit here is the earlier time, T1. We're going to get a Q of T1, and then we're going to get a Q of T2. Over here, it doesn't make a difference. These are just numbers. But as you can see, this is always going to be equal to that anyway. So we've now related the time ordering in our amplitudes that we use in the scatterings to a path integral where we just have numbers. Okay. Now the next thing we want to do we want to talk about adding forcing. I'm going to start this on the next video. Thank you.